Okay, moving on, in this video, we'll do some questions related to the equation of Q equal to mc delta T, which, well, in IGCSE, maybe you were using E equal to mc delta T. Again, it is the same because here, the energy we're referring to is simply heat or thermal energy. Just to quickly remind you again the use of this equation, this is used apparently when there is a change of temperature. That's why you can see delta T. And the equation, it doesn't matter if you use Kelvin or degrees Celsius, as we just now in the previous video we learned that it is the same anyway. More importantly, it's about specific heat capacity. One thing about specific heat capacity is we have a unit for that, of course, and you can deduce the units by rearranging the equation, which simply this equation. So since Q equals to mc delta T, then you could have Q over m over delta T equal to C. So using this, you can devise the units of it. Do you know how to do it? Let me try to you. So remind you again, if you want to express the unit of something, you can use this bracket equals to units of C, which is and therefore that should equals to energy is joule, mass is kg, and temperature change could be Kelvin or degrees Celsius. So let's just use Kelvin here. So you can use the symbol like this as a unit. More formally, we would like to use the order of magnitude. So the index, that means, yeah, like this. Some people may like to use joule per kg using the slash. That's fine. But then if you express like this, then I will be disappointed because I should have reminded you in IGCSE that this is ambiguous because we don't know this k is multiplying or dividing the previous part. So it will be the best if you could put a bracket like this, or you can put a slash on this also. Okay, so I think maybe this will be very clear in this case. Alright, so if you are asked about the definition of specific heat capacity, as you know, they like to ask you about definitions, then you can use this equation to help as well. So basically it means how much energy or how much thermal energy, more precisely, per unit of mass, per unit change of temperature, then that will equal to specific heat capacity. Okay. The other concept, again, before we do calculation, is that there is another terminology called the heat capacity, which again you have learned it in year 9, and just a refresh on the knowledge. Heat capacity and specific heat capacity, apparently it's just missing the word specific. So we would use the symbol big C to represent heat capacity, while specific heat capacity, you know, is small c. If simply you ask me to use an equation to represent, it could be big C equal to m times small c. So therefore you can see that heat capacity means you have already factored in the mass to the object. Let me give you an example. Normally if you have a bucket of water, let's say it is 2 kg of water, then for the specific heat capacity, because it's water, right, the nature of water, then you should remember that, of course you don't have to remember in IB even, but then I suppose all physics students would remember this number at least, 4,200 joule per kg per Kelvin, right? And again, it doesn't matter how many kg are there because the nature, the material itself is water, and so it should be 4,200. Of course, it would also depends on the water content itself. I mean, some people may do their IA, which finding out the different concentration of salt, different concentration of sugar, how that affects the specific capacity of the solution, actually, no longer water. Anyway, those are very boring IA. I don't actually recommend you to do that. And so this is the nature anyway for the water. As in, if you talk about heat capacity, okay, I try to put the abbreviation here to make you easier to see. Then in this case, it will be 4,200 times 2, because if you remember the equation here, and that means it will be 8,400 joule. What's the unit? Joule per Kelvin in this case, because the mass already factor in, so you don't have to put per unit mass here because it's already multiplied into it. Okay, and therefore it means that if you want to increase this bucket of water, 2 kg of water, by 1 degree or 1 Kelvin temperature, then you have to input 8,400 joule into it, and therefore the temperature can increase by 1 in this case. Okay, so depends on the question. Sometimes they might really use the word heat capacity. And I think that's all you need to know about this equation. So without further ado, let's try to take a look of the example 3.2 and 3.3. So on your question set, you should be able to see it. So now I would like you to try it. Pause the video and we will continue. Okay, so first of all, let's take a look of the question together. It said a quantity of heat that much amount absorbed by iron. This is the mass, so I would put down Q, M, and specific heat capacity, which is C, next to it. And it asks you to calculate the temperature increase, so basically delta T. So I think quite straightforward. You use the equation that we just talked about, and then just substitute everything you know. So M is 1.8. C, since it's iron, you look at the diagram, 450. Just one thing you may want to double check is when you see the number, check the unit also. Sometimes, especially if you just simply Google it, in maybe some other discipline, maybe like engineering, or some other discipline, or maybe chemistry, they would use gram sometimes. So you may want to check carefully whether or not it is the SI unit that we use in physics. So delta T is unknown, and you just use your calculator. That would be 12.0987, and you will round it up to 12.1. Or actually, if you have 2 SF, then I would say just keep it as 12 then, right? 12 Kelvin or degrees Celsius, both are fine. Part B is that the heat is now removed from that much of water, which are initially at this temperature, and then you got the specific capacity. Fine, okay, so very simple. I'll use maybe another color for part B. So simply you'll be using the same equation, and now it is the same amount of energy. I think somehow they want to frame the question as in the energy given by the water is transferred to the iron. So I think that's why the energy is the same, but there's no part C, I don't know why. Anyway, so 3.2, C is 4,200. For delta T, remember for delta T, whenever you talk about change of something in mathematics or physics, it's always the nu minus O. That will be the change. As if you, for example, you got $100 originally, and now you have given $50, and that means you have now got 150. So what you do is 150 minus 100 give you positive 50. So positive means you are given $50. Okay, so here's the same idea. Then that means you have to use the final temperature minus the initial. Initial was 48 degrees, so let's just say 48. So just solve the equation. So you have 0.729167 equals to F minus 48. So F would then be plus 48.73. I will actually round it up to 2 SF, so 49 Kelvin in that case. So that will be the answer. So that means if you try to mix the iron with the water, and if that is how much energy is transferred, then yeah, water would actually lose 1 temperature while iron would have gained 12K in such mass. Okay, but this is quite arbitrary, so of course just a feeling of how materials will interact. I think the takeaway other than just calculation is water has a large specific heat capacity, while iron, as you can see, is about 450. So you can see the ratio is about 1 to 10. So if the mass is the same, then for 1 kg, for 1 temperature, unit temperature of water change, for iron it would be like 10 times, almost 10 times. So that's why you can see the change is almost 10 times here. But of course the mass will also matter here. Anyway, let's take a look at the next question. So if you haven't done that, please do it now, and we'll try to do it together now. We have got the mass of the iron, temperature, initial temperature, and then drop into water with such temperature. Find the final equilibrium temperature. Okay, so this is actually a question about mixing. Okay, which it may be the first time you see it, and if you don't know how to do it, I think that's totally fine. So what you do is whenever you have a temperature, like two things mixed together in thermal physics, quite likely what you have to do is to write, since energy conserve, law of conservation. So energy loss equal to energy gained, or you can use Q as well. So apparently you have to use mcΔT for both objects. And I could actually put better iron, W for water, water. Okay, it will be easier to distinguish. And this is a mass for iron, which if you try to turn it, it will be 0.2. If you are not familiar with maths, then you can do 200 divide 1000. For C, you know it is given as it's 450. Delta T, again, final minus initial. So take a look here. Temperature here is 300 and water is 20. So think about that. When you mix them, the temperature logically must be between these two. So between 300 and 20. So apparently what you have to do is the final minus, actually you just have to do final minus initial. And then on the other side is 1 kg, and then you could do 4200, and then again final temperature minus initial. Okay, so there are some people do it in the other way. So for actually I think this is not a preferred way. The most preferred way that you could do is like this. Alright, energy loss, energy gained, add together equal to 0. I think I should teach you using this way too, you know, maybe give you more inspiration, because the way that I did just now is more like how you did in IGCSE. So let's try to do it in more IB way. So the way I do here is since, you know, again, energy loss, energy gain would equal in magnitude, but if you try to think about the plus or minus sign, it's actually the opposite, right? So one of them must be positive, one of them must be negative. So when you try to add them together, it will still be 0. So in this case, then I think it would be the best to stick with this approach, and this should be able to solve all the situation for you. In the future, you may see there are like different cases where you may have mixed ice with steam, then these will come into handy. anyway. Okay, let's just try to do it for now. So we have 0.2, so 90F minus 27000, and then 4200F minus 84000. Okay, and then you just solve the rest, which I can do it slowly. Equals to 111,000. And so final temperature would be 25.87, so run up to about 23. Okay, I assume this is 3SF also, this is 20.0. Then I assume, of course, 25.9 degrees Celsius. Okay, so that actually makes sense because it is between 300 to 20, and we should see it should be closer to the temperature of water, which is 20 degrees Celsius, because again, water first of all has a greater mass than iron in this case. Second thing is, again, the nature of the specific heat capacity is higher, so you can imagine water is a bucket with a greater volume. This is an analogy. Think about this. When you have specific heat capacity, maybe I can draw on the textbook, is that you could have, if this is water, the energy you give in is like, sorry, this is a bucket, and water, this is a bit strange to say that, but the energy you give in is like pouring the water in, and so water by its nature is a bucket with a wider base, so then the increase of the height will be not as much when the base is bigger. While for iron or some other metal which are usually quite low in specific heat capacity, then what they look like will be like a narrow bucket, where if you try to pour the water into this bucket, then for iron they would increase much more in terms of the height, and the height is simply means the delta T in that case. I hope that can give you an analogy on how it looks like. Okay, so this is the basic use of the equation here.